Hello class, welcome to another video in the calculus series. So we're looking at lesson 10, product and quotient rules and higher order derivatives. So in the previous lesson, 9, we looked at basic rules for derivatives. So we looked at some shortcuts. So we're slowly building up our repertoire of tools, of rules for derivatives without having to rely on the limit definition, right? So we're going to look at how to do products and quotients. So how do we do that? So remember that in the previous lesson, we mentioned that you can take the derivative of a sum or difference of functions by taking, by differentiating the functions separately and then adding or subtracting them, right? So for example, here I have a sum of two functions, f of x and g of x. I can take the derivative with respect to x. And that just involves taking the derivative separately and then adding them, right? So you could do this with sums or differences. However, this does not seem to work for products or quotients. So for example, if I have product of two functions, f of x times g of x, I cannot simply take the derivative of both of them and then multiply them together. That's just not going to work. All right, so most of the time it's not going to work this way. So what do we do? So we're going to need to come up with a rule, and we're going to come up with the product rule by using the limit definition. So recall that definition of the limit. So here we go. But once we use the definition on the limit definition and we come up with the rule, we don't have to use the limit definition anymore. But here's a reminder of how to do the limit definition. And so if I multiply two functions, f of x and g of x, then it's simply going to be well, basically I have to take this definition and apply it with g of x, right? So it's going to be f times g, right? So f times g, and then you have the g of x plus delta x, right? So that's that part right there. So that's how we get the second line. And then next what we're going to do is we are going to introduce another term. So this term in red is what we're going to introduce. And the reason why we're introducing this term, notice that if I add these together, I get 0, right? So they cancel out. So it doesn't do anything to the expression. But we're going to add this because it's going to help us simplify this quotient a little bit, okay? This fraction that we see here. And next we're going to split this up into this component and this component, all right? And that's what we do in the second line. And next we're going to split this up into this function and this function right there separately. So we're going to split this up into two separate things. And actually what we're going to do, now that I think about it, is we're going to, so you see that this has an f of x plus delta x. So we're going to actually pull that out. So instead of necessarily having to split it, what we're going to do is we're just going to pull this out. So we're going to factor it out. And so we got this on the outside, and we don't have to necessarily split this because we can leave it like that, because what we're going to do is we're going to distribute this limit to both of these. And when I distribute the limit, well, this is going to turn into the derivative, because the limit of a difference quotient, we got ourselves a difference quotient right here, is the derivative. Okay, so we're going to we're going to distribute the limit here and here and here and here. Okay, now in this one we end up pulling out the g of x, right? So we end up pulling that out, factoring that out. And notice that this right here, that's the limit definition that we have right here, right? That's the definition of the derivative. So this actually turns into f prime of x. And this is the definition of the derivative as well, but for g of x. So this is going to turn into g prime of x, okay? So here we go. So now we have, and then if we plug in 0 into here, well, that's just going to turn into f of x. Okay, so we got f of x times g prime. This is my g prime here, plus g of x times f prime of x. If we rearrange this a little bit, we could get f prime of x g of x plus f of x g prime of x. And this is the one that we're going to use. Okay, so that's the one that I'm going to take as the product rule. All right, so now we kind of derive what the product rule looks like. So let's put it together in a theorem. So theorem 10.1, the product rule. The product of two differentiable functions f and g is differentiable, and we can get it by following this rule, right? So the easiest way to think about it is take the derivative of the first function, leave the function multiplied by the other function, and then add that to the derivative of the other function multiplied by the original first function. Okay. So remember to alternate with the derivatives. So here to do the product rule, just alternate the derivatives. Start with the first one, and then after the sum, differentiate the second one. So you can apply this to more than two factors. So if I have f of x, g of x, h of x, well then I alternate the derivative, right? So I take the derivative of the first one, and then I take the derivative of the second one next, and then I take the derivative of the third one, right? And then I do a sum, and of course I got to multiply by the original functions, right? So that's how you do the product rule, and you can do this for two or more factors. All right, so that is the product rule. So now we're going to go ahead and use it. So let's find the derivative of the following function. So here we got a product, 3x minus 2x squared times 5 plus 4x. So again, since it's a product, we can use the product rule. So we're going to take the derivative of the first part and then take the derivative of the second part after, right? So that's this part right here. And then add them together. All right, so the derivative of the first part, well, the derivative of this is 3 minus 4x, okay? So remember, we got to use the power rule here, right? So bring down the 2, so it's going to be 2 times 2 is 4, and then subtract 1 from the power. That becomes 4x to the 1 power. And if I use the power rule here, do the same thing, subtract 1 from the power, and I get just 3. 3x to the 0 power, which is 3. And then I just rewrite this, right? Just multiply. And then if I take the derivative of the second one, well, the derivative of a constant is 0. So this goes to 0. The derivative of 4x is 4. So here we got 4. And then, we clean this up a little bit. So what I'm going to do is I'm going to distribute this to get, so 3 times 5, 3 times 4x, so on and so forth. So, and then I get this expression. And then I'm going to distribute the 4 here and here, and then combine my like terms. So again, I'm going to combine my negative 16 and negative 8, my negative 8 plus 12, and so on. And this is my solution. And notice that you can get the same solution by foiling. So if I FOIL this and then I take the derivative, so let's show you that. So suppose we, instead of doing the product rule, we decide to FOIL, right? Or distribute. So we got 3x times 5 is 15x. And then we got 3x times 4x is 12x squared. We got negative 2x squared times 5 is negative 10x squared. And then finally, negative 2x squared plus 4x is negative 8x to the third. If I combine these like terms, I get 15x plus 2x squared minus 8x cubed. And then I can go ahead and take the derivative. So I use the power rule. So I get 15. The derivative of x is just 1. The derivative of x squared is 2x, so this becomes 4x. The derivative of x cubed is 3x squared, so then we got 3 times 8 is 24, so 24x squared. Well, if you notice, it's the exact same solution that we have here, okay? So again, why do we use the product rule? Well, sometimes it's easier to use the product rule rather than having to FOIL and then do the derivative, okay? So either way, you get the same solution. So for example, here's a product rule here. This one you can't just easily simplify. So for these kind of cases, it's very useful to employ the product rule. So here we have a product of 3 functions, x squared, sine of x, and cosine x. So f of x, g of x, and h of x, if you will. So let's go and take the derivative. So let's take the derivative of this part first, and then this part, and then that part separately, right? And then take the product and then add them. So the derivative of x squared is 2x, and then just multiply by sine cosine, then alternate the derivatives. So the derivative of sine is, well, it's going to be cosine. And then the derivative of cosine is negative sine. All right, so we're just going to put that together. Let's multiply those. So the derivative and then add them together, and we get to this. We can pull out the x squared here, so that's what I'm going to do next. I'm going to pull out the x squared. And this is what we get for the solution if I pull out the x squared. But you can also simplify and use a identity for that. This is equal to cosine 2x. That's an identity. Cosine of 2x equals cosine squared x minus sine squared x. That's just an identity. You don't have to use the identity. You can just leave the answer as this. That's fine. But I like to simplify things a little bit. So this is the most simplified for that. Of course, you can also pull the x out because they have an x in common. But there's really no need to do that. All right, so here we go. We got the product rule down. Now we're going to figure out what if I have a quotient. If I divide two functions, how do I get the derivative of a quotient? So again, just like with the product rule, I can't simply do the derivatives of the function separately and then divide them. That's just not how it works. So we're going to have to come up with a rule for this. So remember the actual definition of the derivative, right? Given above. And now we're going to do the quotient of f of x and g of x. Well, if I do a quotient, then this has to be divided by g of x, right? And then this has to be divided by g of x plus delta x. If I use that definition of the derivative, right? Where this is f of x, g of x. So that's what I have in the numerator here, right? Over delta x, of course. And then we're going to combine the fractions. So we're going to combine the fractions like so. Now remember the least common denominator of this is taking the product. So for example, this is missing a g of x plus delta x, right? So I'm going to multiply by that top and bottom. And that's how I get this term right here, right? And then this here is missing, this first fraction is missing a g of x. So if I multiply by g of x top and bottom, that's how I get this part right here. And then I can combine them under one common denominator, which is g of x and g of x plus delta x, okay? Now I can move this down with the delta x and just move it down to the denominator. So now we got, three factors on the denominator. And then we're going to use a little trick. Remember the trick that we did with the product rule where we introduced a couple of terms in the middle? Well, we're going to do that here. We're going to introduce the f of x, g of x, and then f of x, g, the negative and positive. So again, this doesn't do anything to the expression because it's 0, right? It's plus and minus the same thing. But you can see that it's going to be very useful when we split this up. So we're going to, basically what we're going to do is we are going to take this part right here and we're going to pull out a g of x. So you see this g of x that they have in common? We're going to pull that out, all right? And that's what we have here. G of x is on the outside. And then you get this fraction here, right? And then we're going to pull out an f of x from here. So pull that out, and then we get this right here. And when we do that, we get two fractions, and these are difference quotients. That's exactly what we want. And we're gonna split the limit. We're gonna distribute the limit to here and to here, right? And figure out what that is. And we can also put the limit on the bottom as well. So we're gonna do the limits all the way around, all top and bottom. But then we know that this is f prime of x, right? That's this guy right here. So that's f prime of x, and this guy is g prime of x. All right, and then if I plug in delta x is 0 here, then that becomes g of x. This goes to 0. So then g of x times g of x is g of x squared. So we end up getting g of x f prime minus f of x g prime of x over 2 g of x's, right? So it's to the second power. And that is my quotient rule. This should say quotient rule, not product rule. So I apologize for that. It should say quotient right there. All right, so that is the quotient rule. So so quotient rule is the quotient, the derivative of a quotient of two functions is as follows. You take the derivative of the numerator function and multiply by the derivative function minus. You take the derivative of the denominator function multiplied by the numerator function divided by the denominator function squared. All right, so here's a tip to remember. This is how some students remember the quotient rule. They say that the top one is the high and the bottom one is the low. That makes sense. One is on top, one is on bottom. High, low. And then you say the rules is as follows: high d low minus low d high over low low. So high d low d high, low low. And that's an easy way to remember. This is going to be the squared right here. High d low, the d stands for the derivative. So that's when you do the derivative of the low function, right? All right, I wanted to fix this real quick. So I had a little mistake on the slide. So it was, these were switched in the original. In the original here, these were actually switched. So I went ahead and corrected it. So it's low d high d low over low low. So you take the bottom function, which is the g of x, right? That's the low, times the derivative of the high function, the derivative of the top function, minus the top function times the derivative of the bottom function over the bottom function squared. So if sometimes some students use ho instead of low. So high over ho d high minus high d ho over ho ho. So another way to remember it. I just, you can use either one. And that's just a way to remember the quotient rule. Okay, so here we go. Find the equation of the tangent line to the graph of the given function. So notice it's a quotient, so we're going to need to take the derivative using the quotient rule. All right, so using the quotient rule, remember low d high minus high d low over low low. So again, the low is squared, right? It's low. And then we got low, that's the bottom function, times the derivative d, and then the top function, okay? So just using that template just to help you remember. All right, so take the derivative of this. The derivative of this is just 3. And the derivative of this is 2x plus 5. All right, so we're going to do that in the next step. So that's what we got. And then next, we're going to do is we're going to distribute the 3. Distribute the 3 here and here, and then FOIL this, of course. And we get the next step. And then we're going to combine like terms. So 3x squared minus 6x squared is negative 3x squared. 15 minus 13 is 2x. And don't forget this negative turns this into a positive. All right. And then, we're going to simplify if possible. Usually we leave it like that, and that will be the derivative. And sometimes you can simplify it further. So what we're going to do now is we're going to plug in, we're going to figure out what the derivative is at x equals 1. So remember they give us a coordinate there. So they give us x equals 1, and they give us y equals 1/3, right? So we're going to plug in x equals 1 into the derivative. So, into here for x, right? And we do that, we get 1/9. So that's going to be my derivative, just simplifying a little bit. So my derivative at 1 is 1/9. And then remember the equation of a tangent line is y minus y1 equals slope times x minus x1. And we usually replace the slope with the derivative, right? Because the derivative is the slope of the tangent line. So it's going to be the derivative at x1. All right, well, x1 is 1, right? So we see that this is f prime of x1. This is x1 is 1. And then we got y1 is 1/3. So there's our tangent equation, the equation of the tangent line. Of course, we're going to distribute the 1/9. And then we're going to add 1/3 to both sides. And that's how we get this step here. And then negative 1/9 plus 1/3 is 2/9. Okay, so negative 1/9 plus 1/3. Multiply this by 3 top and bottom, so that becomes negative 1/9 plus 3/9, which is, of course, the 2/9 that we got over here. So this is the equation of my tangent line. All right, so what about trig functions? So like tangent, cotangent, that so on and so forth. Well, to figure out what the rule is for the derivative of tangent, we know that tangent is sine divided by cosine, and cotangent is cosine divided by sine. So this is what better lesson to do the derivative of this than this lesson where we're doing the quotient rule. So we're going to use the quotient rule to find the derivative of tangent. Okay. So again, we got to do low d high, right? So that's the first part. So cosine x times the derivative of the high function. Well, the derivative of sine is cosine, right? And the derivative of cosine is negative sine. So we got cosine times cosine, negative sine x, minus sine x times negative sine x. And so we got cosine squared x plus sine squared x. And remember that this is equal to 1. This is the Pythagorean identity, right, for sine cosine. So that's equal to 1. So we get 1 over cosine x squared. And then we can rewrite that as secant squared, because 1 over cosine is secant. So the derivative of tangent is secant squared. Now let's do the derivative of cotangent. So again, using the low d high, right? Low and then d high for the first part right here. Well, the derivative of cosine is negative sine, and then the derivative of sine is cosine. So we got the next step here. Oh, I forgot. I I didn't, so this should actually say, hold on, this, I don't know why I have this here, so that's a typo. That should be cosine times cosine, so it's going to be cosine squared. Or let me actually, this should be cosine. This times cosine. All right, so in that case, that's going to be, this is going to turn into negative sine squared x on the top minus cosine squared x. And then I can pull out the negative. So if I do that, I get this. I pull out the negative there. And we know that this should be a squared right here. We know that this is a Pythagorean identity, so that becomes 1. So it becomes negative 1, right? Because of the negative on the outside. So negative 1 over sine x squared. But remember that 1 over sine is cotangent. So, or, sorry, it's cosecant. 1 over sine is cosecant. So this is going to be negative cosecant squared. So now we know the derivative of tan is secant squared. The derivative of cotangent is negative cosecant squared. All right, we can also do this for secant and cosecant. Remember that secant is 1 over cosine, cosecant is 1 over sine, right? That's what we mentioned earlier. So we can use the quotient rule in order to take the derivative of this. We can also use the chain rule to do this, right? I don't remember if we did the chain rule in, well, actually, we haven't learned how to do the chain rule yet. So the chain rule is going to be in the next lesson. So chain rule is the next lesson. But so far, all we've done is basic rules and product and quotient rules. So we're going to show you how to do this with the quotient rule. So remember, the low function is cosine, the high function is 1, right? So we got to do low d high. Again, I'm not sure why I have sine here. This should say 1. There's a lot of typos here, so I apologize for that. So it's low d high, the derivative of 1. Well, the derivative of 1 is 0, right? So that should just be 0. And then minus high d low. So then the derivative of cosine is negative sine x, right? So if the derivative of this is 0, then this goes away, right? That whole term. So we got cosine times 0. And then negative 1 times negative sine is positive sine. So we got sine x over cosine x squared. All right, and then we're going to split this up into sine over cosine and then 1 over cosine. So notice that there's 2 of these, so it's squared, right? But we just split it up. And then we know that this here is tangent, right? And we know that this here is, well, it's secant, right? So the derivative is secant x tangent x. So the derivative of secant is secant tangent. All right, so now we're going to do the derivative of cosecant, which is 1 over sine. Again, using low d high. So we got the low and then the derivative of the high. Well, this turns into 0, right? The derivative of sine is cosine. So we got negative cosine. So this goes away. We got negative cosine over sine. And then we can split that. So this turns into negative cosine over sine x squared. Okay. Then we can split that up into this, which this is cotangent. And this is cosecant. And don't forget that negative. So it becomes negative cosecant cotangent. All right, so that's your derivative of cosecant. All right, so now we're just summarizing the derivative. So now we know the derivative of tangent, secant squared. We know the derivative of cotangent, it's negative cosecant squared. Derivative of secant and derivative of cosecant. So just summarizing what we got for theorem 10.3. All right, so we derived those. Now we know what they are, so we can just use them. All right, so let's go ahead and use those rules and employ them. So differentiate the following functions. So they involve some trig functions in them. All right, so the derivative for the first one, well, the derivative of x is 1, right? And the derivative of tangent is secant squared. So that's it. So it's just going to be 1 plus, this should be minus, not negative. So that's a typo there. It's 1 minus secant squared. The derivative of tangent is just secant squared. So it becomes 1 minus secant squared. All right, now for part B, we need to use the product rule. So remember, do the product of the first one times the second one plus the derivative of the second one, right? Times the first one function. So the derivative of x is just 1, right? So it's just 1. Then alternate, the derivative of secant is secant tangent, right? So this is my secant cotangent. All right, that gives you part B. Part C, we need to use a quotient rule, right? So low d high minus high d low. So we got the low, which is x squared minus 1. Then we got to do the derivative of the high. So what's the derivative of cotangent again? Well, the derivative of cotangent is negative cosecant squared x, right? And then we have the 3 there, so it's going to be negative 3 cosecant squared. And then what's the derivative of x squared minus 1? Well, this is just going to be, the derivative is 2x. All right, so we do plug that in, and we get the following quotient. And then, you know, we can simplify a little bit. So what I'm going to do is, I'm just going to go ahead and multiply. So we got the 3 times 2 is the 6 right here. And then we just pulled a negative 3 out to the front there, to the first term. All right, and there's your derivative. There's your derivative using the quotient rule. All right, so the next thing we're going to look at is higher order derivatives. So up to this point, we've only done the first derivative, right? We've only done the derivative one time. Now, higher order derivatives means you take the derivative multiple times, right? So not just once. You can take it twice or thrice or more, right? So here we go. So the first derivative we call y prime or f prime of x or dy dx, or the derivative with respect to x of f of x. So these are just different ways to you know, use symbols for the first derivative. Now, when you do the second derivative, instead of having just one prime, you're going to have 2 primes, right? So it's y double prime or f double prime. Or you see the 2 here, right? So that's the d2y and then dx2, okay? So notice that you're differentiating twice, right? Well, that's what it stands for. That's not an exponent, right? It's just telling you that you're doing the second derivative. So it's not technically an exponent, right? It's just a second derivative. All right, so notice that the 2 is in front of the d here in the numerator, but it's in front of the x on the denominator. All right, so just keep that in mind. It kind of alternates. All right, so the third derivative is y triple prime, right, with the 3 apostrophe symbols, and then or d3y dx to the third. So again, this is read as a third derivative of y with respect to x. And then you got the fourth derivative. Once you get to 4 or higher, we use the parentheses, right? So that way we don't confuse it with a power, because if we do it without the parentheses, it looks like y to the 4th power. So if we do a parentheses, it kind of tells you, hey, we're doing the derivative of this, not raising it to the 4th power. All right, and then nth derivative, we just put on, you know, anything for n, 4 or higher. Okay, so that's the notation for higher order derivatives. Now in physics, this is actually interesting, right? So we know the position function is s, right? Or is usually x of t, y of t, and sometimes we use r of t in physics, right? So the position function is just the distance, right? So what, you know, where is it located in time? So usually it manifests itself as like a distance function, right? The velocity function is the derivative of position, right? So the velocity is the derivative of position. So here we go. So we got velocity is the derivative of the r, right? Or the derivative of x or y. The acceleration is the derivative of velocity. All right, so acceleration, a of t, is the derivative of velocity. But we know that the velocity is the derivative of r, right? So what it looks like is, okay, so we got dv dt, right? That's what a is. But then we know that v itself is dr dt, right? So actually, let me just rewrite it this way. So I'm going to put the v off to the front, and I get this, right? So notice that these are equivalent, right? And then I'm going to replace v with dr dt. All right, so you can see that we have the 2 d's, so that becomes d to the second, right? And then we got dt twice, so it becomes dt2, right? With the 2 there. So the second derivative of r with respect to t. That's how we get that, the second derivative. All right. So then now we know velocity and acceleration. Now there's some other interesting higher order derivatives. Did you know you can take the derivative of acceleration to get what's called the jerk function? So the jerk function j of t is the derivative of acceleration. But remember, we said that that acceleration is the second derivative we know that acceleration is the second derivative of position, right? So we got this. And then, so then we have three of these, right? So it's a third derivative, the third derivative of r with respect to t. So we got the three there. That's how we get this. And then we got the snap function, which is the derivative of the jerk function. So it's the second derivative of the acceleration. It's the third derivative of velocity. It's the fourth derivative of position. Then we got a crackle function, which is the third derivative of acceleration with respect to time, fourth derivative of velocity, fifth derivative of position. And we got the pop function, the fourth derivative of acceleration, the fifth derivative of velocity, and the sixth derivative of r with respect to t. So these functions are used in specific applications. They're not used in in a lot of things. They're just used in niche applications, but they're there regardless, and we use them in some applications in physics. So something interesting. They have interesting names, but they do have some applications. So just kind of showing you the applications of higher order derivatives. All right, so here we go. So let's look at finding the second derivative of the following functions. So we got three functions here. All right, so the derivative of the first function is, well, we use the power rule. Power rule here, power rule there, bring the power down. So you get 4x, and don't forget to subtract 1 from the power when you use the power rule. So we have 4x to the third power, 6x, we get 2 times 3, which is 6, right? So 6x to the second, and then 3 times 2 is 6, so 6x to the first. The derivative of x is just 1, right? All right, and then we take the second derivative of that, and so we use another power rule, right? So bring the power down, subtract 1, of course. And so remember, the derivative of a constant is 0. The derivative of x is 1, so that just becomes 6. And then so we get 12x squared plus 12x minus 6. So just use the power rule twice. Now for part B, we got to use a quotient rule, right? So remember, low d high, and then minus high d low. So so the derivative of x is 1, right? The derivative of x minus 1 is also 1. So it's actually an easier derivative. So we got the derivative here of this is the derivative of x, and then this here is the derivative of x minus 1. But in any case, we get negative 1 over x minus 1 squared. And then we are going to do another quotient rule for that, and this time we got to do low d high, so we got to take the derivative of negative 1, but the derivative of negative 1 is 0, right? So this turns into 0. And then the derivative of this guy, this is going to be 2x minus 2. All right, so that's how we get this here. All right, and there is, and actually there shouldn't be a squared here, so let me get rid of this. It should just be x minus 1 to the fourth power. Now, the reason it's to the fourth power, right, is because remember, it's low d high over high, so it's low d high minus high d low over low low. So this is the same thing as low squared, right? So this is just to the second power. So but this is already to the second power. So when I do this to the second power, it's x minus 1 to the second power raised to the second power, which turns into the fourth power. Okay, so that's why I have to the fourth power there. All right, so hopefully that clears that up. So that's the second derivative for the first one. And then notice that we can actually pull out an x minus, or we can actually pull out a 2 from this here. And if we do that, then one of these cancels, right? So leaving me with 3 on the bottom. So this is the simplified form. All right, so then let's take the derivative of the third function. Well, the derivative of secant x is secant tangent. We derived that earlier. Then, in order to do the second derivative, we have to use the product rule, okay? So remember the product rule. The product rule is f prime g plus f g prime, okay? So you alternate the derivatives, and then you take the sum. And then, obviously you multiply them by the original functions. So here, this is the derivative of secant. So let me make sure I make this clear. That's the derivative of secant, and then times tangent right there. All right, and then the next part is the derivative of, this part is a derivative of tangent, which is secant squared, and then times secant, right? And that's how we get it. We just multiply them. This is going to be to the first power time, and then to the second makes to the third power. Right? And this is our derivative. All right, so we're gonna, for the final example, we're gonna look at a differential equation. So a differential equation is an equation with derivatives, okay? So remember, when you see the word differential, that's like differentiate, which is like derivative. So this is the first time I believe seeing a differential equation in this series. So like I said, differential equation has derivatives. So this has a bunch of derivatives in here. Third derivative, second derivative, first derivative, right? So we are going to, we're not going to solve this differential equation. We're just going to see if this is a solution to it. So in order to do that, we need to do the third derivative of this function so that we can plug it into here, right? And then the second derivative and first derivative. So that's what we're going to do. Okay, so let's go ahead and take the derivative. So we're going to take the derivative of this. So we're going to use the power rule. So if I take the derivative of this, I got to bring the power down and then subtract 1. The derivative of x is just 1, right? And the derivative of a constant is 0. So it's going to turn into 6x squared minus 6. And then to find the second derivative, I got to take the derivative of this first derivative. So use the power rule. The derivative of a constant is 0. So we get 12x. And then find the third derivative of that. Well, the derivative of x is 1, right? So it's going to be 12 times 1, which is 12. That's our third derivative. And then next, we're going to plug those into the function here, here, and here. And by doing that, so we get negative 12 minus x times the second derivative, which is 12x, minus 2 times the first derivative, plus the 24x squared that was just kind of hanging out there. But now if this is going to be negative 12x squared, then this is going to distribute, right? So I get negative 12 minus 12x squared minus another 12x squared, and then this double negative here to makes that plus, right? Because we got this 2 negatives there. And then plus 24x squared. But now you got negative 12 plus 12 is 0. We got this is negative 24x squared, right? Which cancels out with this. So we end up getting 0 out of 0. So everything cancels. And therefore, this is a solution to the differential equation. So it satisfies the differential equation. All right, guys, that's going to do it for the video. I hope you found this useful and informative. And as usual, I'll see you in the next one.